Hello and welcome to our module on the dissociation constant. Today we'll be covering what the acid dissociation constant actually is, and we'll also be looking at how this relates to the relative strength of an acid or base. So before we do some questions and I explain what the acid dissociation constant is and the formula and stuff, I'd like to set the scene. So I have two examples here. The first equation is a strong acid, hydrochloric acid, dissolving in water. The second example is a weaker acid, acetic acid, dissolving in water. As you may recall from an earlier module, stronger acids, such as hydrochloric acid, dissolve into protons in solution a lot better than weaker acids. So what do I actually mean by this? If I were to have 10 moles of the hydrochloric acid, it is more than likely I'll have near about 10 moles of H3O+, as they're in a 1-to-1 ratio. However, if I have 10 moles of acetic acid, I will not get 10 moles of H3O+, as acetic acid is a weak acid, and it does not protonate to the same extent as hydrochloric acid does. In this way, the acid dissociation constant tells us how much an acid likes to protonate in solution. We're going to draw on this a bit later, but it gives us a relative scale of how strong an acid or a base actually is. So don't freak out with this page, but these are some very important associations we have that will become a lot more clear at the end. So we're going to revisit this page at the end and it'll become a lot more clear. But I want you to keep in mind some of these really important associations. The first one I stated a bit earlier. So the magnitude of the Ka, so the Ka is something that we use to represent the dissociation constant for the acid. Conversely, as you might have guessed, there's a Kb, which is the dissociation constant for the base. So the magnitude of the Ka gives us a quantitative measure on the strength of the acid. So it actually puts a number on how strong an acid is. We can use these numbers to kind of compare the strength of an acid. Instead of just saying HCl is stronger than acetic acid, we actually have a number to show for it. And I'll show you how to calculate that a bit later on. So the larger the Ka, the stronger the acid, which means the more it can protonate in solution. The smaller the Ka, the weaker the acid. If you look at this diagram in red here, so everything down the bottom would obviously have a very high Ka because these are examples of strong acids. Everything at the top would have a very low Ka. Conversely, the magnitude of the Kb, so base, dissociation constant of the base, gives us a quantitative measure on the relative strength of the base. The larger the Kb, so everything up the top here would have a very large Kb because they're strong bases, the stronger the base. So the more OH it can generate, or protons it can accept in solution. The smaller the Kb, the weaker the base. Everything down the bottom here. pKa and pKb is the negative log of Ka and Kb. All that means is you calculate the value of the Ka or the Kb, and the pKa and the pKb would just be the negative log of that value. We don't really use the pKa or pKb, and it's not entirely relevant in your studies, except it may come up in some harder questions. But if you were to use them, it's because the Ka and Kb are usually very, very complex numbers. So it's like 1 times 10 to the power of minus something. Whereas the pKa and the pKb would just be a nice two decimal number, if that makes sense. So they're smaller, easier to comprehend numbers. If we're taking the negative log of something, that flips. So the smaller the pKa and pKb, the stronger the acid and the base, respectively. Now, I want you to remember, for your exams, it's very high yield. You understand the Ka and the pKa. Our discussion of the Kb and the pKb is entirely just for your understanding and on the odd chance that you get a convoluted question. But 9 times out of 10, you'll get a question on the Ka and the pKa. So really try and hone in on these concepts. In the second part of this video, we'll be covering how to calculate the acid dissociation constant using some worked examples. However, before we do that, it's very important you not only understand, but memorize this very important formula. Especially in chemistry, but all your STEM subjects for that matter, it's important you understand what variables you have. So I introduce you to 3, the Ka, the pKa, and the pH. It's important for you to understand how to not only calculate those 3, but also how to get in between. So going from the Ka to the pKa, the pKa to the pH, and the pKa to the Ka, if that makes sense. So we'll get stuck in. For the equation HA, so HA being our acid, dissolving in water to form H3O plus the A minus, which is just the negative ion for the acid. To calculate the Ka, it would be the concentration of H3O plus times A minus all over the concentration of the acids. A neat way I like to remember this is pour or products over reactants, because I used to get the order mixed up. I'd always put HA on top and everything at the top here on the bottom. Disaster, lots of marks cost, so don't make that mistake. As I said before, pKa is nothing but the negative log of the Ka. So ideally, you'd put all these numbers into your calculator. Obviously, they'd give you the concentration of each thing. You put it into your calculator, get some number. So to calculate the pKa, it just would be the negative log of this number here. To get from the pKa to the Ka is a bit different. So if you remember your log laws, it's the same as going from the concentration of H3O plus to pH. So to get from, if you're given the pKa to get the Ka, it's just 10 to the power of minus whatever the pKa value is. So those are 3 very important formulas for you to understand. Using formula number 1 and number 2, we can also draw a very important relationship involving pH. Now, this is going to require you to understand your log laws, but if you want to go ahead and you haven't done logs yet, you can just memorize this here. So the pH equals to the pKa plus log 10, the concentration of A minus over HA. So this gives us a rough indicator. If we're given the concentration of A minus and HA and the pH, we can calculate the pKa and get the Ka as well. Or if we're given the pKa and some concentrations, we can calculate the pH. This becomes extremely relevant when you're calculating buffer systems and their pH. So I'll work through the derivations, my bad. So as we know, the pKa is just the negative log of the Ka, and this is a formula for the Ka. Now using our log rules, this gives us pKa equals negative log H3O plus minus, so we've taken this whole chunk out as the division factor, minus log 10 A minus over HA. This you should recognize as nothing but the equation for your pH. A bit of rearranging gives you this final formula here. This are very high yield for exams. Do not forget them. Number 2 and 3, less so, but still very important to remember. Do not forget number 1 and this one down the bottom here though. As I mentioned previously, the concept of the dissociation constant of the base, so Kb, is not incredibly important for you to understand in answering questions, as it's quite rare that they'll ask you for the Kb. However, in the off chance they do, it's very important for you to remember. So if we have an equation, so B being our base, dissolving in water to give us BH plus OH minus, the Kb, once again, pour products over reactants. So BH, the concentration of BH plus times the concentration of OH minus, all over the concentration of the initial base. pKb, as I said, similar to pKa, is just the negative log of Kb. If you're given pKb to get from Kb, it's just 10 to the power of minus pKb. Another important relationship to get from Ka to Kb, if you're given one or the other, this is probably the only time you'll see this used. You can use this neat trick. So Ka times Kb equals your dissociation constant of water, which we know is 10 to the power of minus 14. These four associations are incredibly not too important for you to remember, but just keep them in the back of your head in case they come up. Number 4, however, is probably the most important of the lot. So to get from Ka to Kb, especially since you know Kw is 10 to the power of minus 14. If you're given Ka, you can get to Kb. So we've gone over the concept of Ka and Kb and how to calculate those using formulas. So now I want to bring your attention to how these concepts, so Ka and Kb, relate to the strength of an acid or a base. So for the formula of Ka, for demonstrations purposes, I'm going to split up this formula in the following manner. So I'm going to make it this. And I want you to bring your attention to this segment here. So the concentration of H3O plus over the concentration of HA. For a strong acid, these two numbers here, so this and this, will be equal or near about equal. So you'll have a ratio of approximately 1. For a weak acid, this bottom number, so the concentration of HA or the original acid, will be a lot bigger than the top one. For example, if I were to have 10 moles originally of my weak acid, I might only generate 5 moles of H3O plus because it can't protonate as well as a strong acid. So for a weak acid, you have much less than 1. Hence, the bigger this ratio, the bigger Ka. And since strong acids, give you a bigger ratio, they'll give you a bigger Ka. Another way of saying this is the bigger the Ka, the stronger the acid. We can do a similar thing for Kb. So Kb, let's split up the formula to look more like this. So I'm going to bring your attention over here again. Similarly, for a stronger base, this ratio here, so the ratio between the concentration of OH minus and the original base B, will be approximately 1. However, for a weak base, if I have 10 moles of the base, I might only get 5 moles of OH minus. Hence, similar to up here, it's much less than 1. Hence, the higher the Kb, the higher this ratio. And since stronger bases have a higher ratio, they have a higher Kb. Another way of saying this is stronger acids tend to have higher Kbs. But it's very important for you to know this relationship up here, so the one with the Ka. That's what's going to be examined. And I promise I'd come back to this slide here, and hopefully makes a lot more sense. So as we learned, the magnitude of the Ka gives us a quantitative measure on the strength of the acid. We know that now. So it allows us to give a number on how strong the acid actually is. And we know the formula for that now. The larger the Ka, The stronger the acid, the smaller the Ka, the weaker the acid. We just covered that in the last slide. The magnitude of the Kb, which you don't really need to know for your exams, but good to keep in the back of your mind, gives us a quantitative measure on the relative strength of the base. The larger the Kb, the stronger the base. The smaller the Kb, the weaker the base. You should know the relationship between pKa and pKb now, and also how to calculate them. And also bear in mind that pKa and pKb are negative log functions. So the smaller the pKa and pKb, the stronger the acid and base, respectively.